Okay, I think we can get started. So today we will talk about the class calibrated label distribution for semi-supervised image segmentation. First, here is a brief overview of the highlights of this paper. It is published in MICCAI 2022. First, about the innovations. So it takes the imbalance of foreground categories into consideration. And to handle this imbalance issue, the authors propose to use a class-aware weighted loss and also use a dual uncertainty-aware sampling supervision during training. And secondly, the authors propose to use random cropping based on a probability distribution instead of regular random cropping. The third thing is the proposed approach achieves very noticeable improvement over the existing state-of-the-art segmentation approach in the semi-supervised learning rigging. And the limitations of this paper are also obvious. The key thing is the segmentation performance, though it achieves very big improvement when you compare it with the existing SOTA models, but its test score is only 87.2. Intuitively, the reasons why this approach works include two things. The first is that the authors define a category-specific loss for each foreground category, so that more precise control can be achieved. And this is achieved in practice by using a weighting scheme. And the second thing is there are two models used during the training process, and for each of them, its prediction can be used as the procedural label to guide the training of the other model to form a training loss. So here is the system architecture of this approach. The first thing is we have an input, then we do a random cropping to get a subvolume of this input image. And this subvolume will be fed to two models, model A and model B. And for each of this model, it will have an output PI, and from this output, the procedural label can be generated for each of them. Then if you consider the model A, its procedural label will be combined with the output from model B to calculate the first unsupervised learning loss. Similarly, for model B, its procedural label will be combined with the output of model A to calculate the second part of the unsupervised learning loss. So totally, we have a unsupervised learning loss like this. And here the running index I is for each image, and each PI is actually the output from the model for each image, and this yi height is the segmentation mask for the ith image sample. So about the supervised learning part. Okay, I think here is for the supervised learning loss actually, because we have the labels here. Here, for example, still, when the label data input comes to this model, we still do a random cropping to get a subvolume, and this subvolume will go through two models A and B to get the corresponding output, PIA and PIB. And each of them will be combined with the ground truth label Y to form a supervised learning loss, segmentation loss. So finally, we have a supervised loss like this. And this is one that, so we have totally NL labeled examples, and we calculate the segmentation loss for each of this model output. Now here is the the big picture of the loss. So we have a unsupervised non-linear loss, and it's calculated via the cross entropy. Here is the x you can treat as the for example the predicted segmentation feature map, and each peak at each spatial location it has a vector, and this vector is the foreground class distribution, and for this y you can treat as the ground truth label, and it's it's also a segmentation. It's a segmentation mask, and each location has a one particular label, each pixel. And this image segmentation problem can be treated as a pixel level classification problem. And for this supervised non-linear loss, so there are two components. The first one is this cross entropy. The second one is this death score loss. Death score is it's calculated in this way. For example, this is the ground truth. Then this is the ground truth, and this is the prediction. Then we calculate the element wise multiplication and do the summation over them, and divided by this term. Okay, let's now talk about the weight control thing, basically the weight for controlling the loss, for scanning the loss. The key motivation for this is to achieve like a category specific control for each loss during the training process. Still, this problem is treated as a pixel level classification. For this part, we need the ground truth label so that we can calculate this weight. Here, this Ni is the number of pixels in this foreground category I. So you can see this Ni is essentially this lowercase ni is essentially the percentage of the pixels in the ith category, and then its weight, its relative weight is obtained by dividing the maximum percentage by each category percentage. And this wi will be used to basically scale the loss associated with the foreground category I. What about the unlabeled data? For unlabeled data, we can also calculate the like a weight and also a sampling parameter. For example, here we can use the procedure label from one model, and for example, this PI is the prediction from the other model. Then we can use them to calculate this UI. This UI you can treat as the uncertainty associated with category I, and this uncertainty will then can be used to calculate this sampling factor SI, sampling rate factor. And this sampling rate factor SI will be used to obtain the sampling mask. Essentially, for example, this SI, when you get this, you will sample a certain number of pixels from category I, and you will only use this certain number of pixels from this category I to calculate the final loss. And this can alleviate the imbalance issue to some extent. So about the empirical result, so here is the one plot showing the imbalance issue. Basically, there are four foreground categories, and there is one background class. You can see this background class has a much more number of pixels, and if you only focus on the foreground categories, there is also an imbalance issue here. So these categories 1 and category 3 have more pixels than category 2 and category 4. Here is an illustration of the dataset for the four foreground categories. So each color represents one category. So this table shows the segmentation performance of the proposed approach on one data set. And you can see this improvement is quite noticeable. And for example, from this, the DICE score can go from 83.6 to 87.2. But if you only look at this number 87.2, it's a relatively low and still far from being able to be developed as a product, a commercial product. Okay, here is an illustration of the segmentation performance. You can see the proposed approach can achieve fairly good segmentation result. This, if you compare it with the CSP approach, yeah, the improvement is pretty good. And they compared it with the ground truth. There's slightly off, yeah, of this yellow class, but overall the performance is pretty good. Okay, that's all. Thank you.